What's it all about? So essentially, EPSRC wanted platforms, and we offered them what we're calling a people platform. So basically, it's about professionalizing research technology professionals. Supporting digital RTPs is effectively is impossible if we can't deliver the necessary training at all levels, beginner to expert, for existing RTPs and the next generation of practitioners. In turn, training has reduced impact if we can't provide attractive roles and widely recognized career development pathways alongside a thriving, welcoming and diverse professional community, which will come as no great surprise to the people in the room, I'm sure. But this is basically what we're aiming to do. It's a bit of a mixed landscape at the moment. So a lot of RSEs are already, it's a profession that's already being developed. There's lots of training already. But this is part of the idea behind this is to try and spread that beyond the traditional RSE, well, traditional, and include other research technology professions as well. I'm sure many of you are already familiar with the problem, and a large part of it stems from academic structures and culture, from the way that people are rewarded in their careers. The traditional kind of research project group might involve one person who's kind of the computer guy. They often work in relative isolation from other people with the same kind of professions who have knowledge that would be useful to share. Ways of working that be useful to share. You're often stuck a bit if you're in one of these roles. It can be a bit of a process of moving from postdoc to postdoc. It's hard to get promotion using the usual kind of academic career progressions. It's hard to get the kind of recognition, and importantly for all of us working in this field, it's about remuneration as well. So what the project's really aiming to do is to develop a more professional, diverse and inclusive research technology community, raise the profile of data and infrastructure roles to complement software. It's not that our research software engineers are living in a wonderland yet, but as new kinds of professions become a bit more developed, there are things that can be learned from RSEs and further development that can take place. We're looking to enhance career opportunities, improve awareness and recognition of these kind of new roles that are coming through. One of the things that's become apparent, I think, in ARC at UCL is that some of the people who actually have these roles, depending on the role they play, can come from quite different sort of backgrounds and so forth. So getting people to understand the different roles themselves and between the RTP community is a useful thing. And we're looking to develop flexible, transferable policy and strategy to support RTPs. That's our lovely graphic. As you can see, the roles that we're looking at are data stewards, research software engineers, and the people who are involved in actual infrastructure development. So research infrastructure developers, research infrastructure engineers, call them what you will. They're the main focus, those three different roles. Of course, there may be sort of different flavors of role between those. I mean, I'm in charge of the data stewardship team at UCL, but we also have data stewards working in the library, for instance, who have a slightly different emphasis on the kind of roles and the function that they serve, but they're very much still data stewards. We have people scattered throughout the departments, as indeed is the case for the RSEs, and maybe to a slightly lesser extent, research infrastructure developers. But there may be slightly different flavors of these things. We're looking at a number of different approaches, which we've divided into work packages. We'll ignore work package 5 because that's just project management. But community and EDI, training and skills, career pathways, and policy and awareness. And just to say a few things about some specifics, as I say, we're only just starting the project, really. We're just getting going on it, but some things that we'll definitely be focusing on and trying to do is to expand the focus of Research Software London to include the other research technology professions, leading a diverse EDR seminar series, engaging with national and international equality, diversity and inclusion initiatives. We're very keen that that's not just paying lip service to diversity, but a significant resource is spent on that. We're looking to develop and run a research technology champions program across the partner institutions. So Imperial have been doing that certainly last year with a number of PhD students who've been assigned across different departments to act as champions for at least research software engineering. We're looking to extend and expand that to the other institutions involved now as well. We need to curate the existing training materials and create new content at basic, intermediate, and advanced professional levels. So that's the bit that me and my team at UCL will be focused on, and Sam will be very much involved in that. That will involve a bit of desk research to start off with, because of course there are training materials for all of these professions, even if they're not necessarily terribly well targeted at the kind of career structures we're really looking for at the moment. But we'll be doing that. We will be analysing what it is in job descriptions that people expect from the various different professions, what the basic, intermediate and advanced training looks like, and then taking a bit of an iterative approach. It's a 4-year project, so we should have an opportunity to try things out and to hone and refine things, to develop career pathways and advocate for their adoption. So there are tentative work in this thing. Some universities now have defined career pathways, others do not. We will be looking to see what works and what doesn't, exchange ideas, try and develop what standards might look like, and try and spread good practice between the different institutions and see what we can do to really bring it about. Interestingly, we were going to be aiming to do some secondments, bridging and mentoring, in particular, not just within, but also between institutions, develop systems by which people can do a little bit of time at some of their peer institutions, work in different environments, find out what's going on, increase their skills and understanding of the environment that way. We anticipate that a lot of the challenge of this is actually not going to be from people doing the jobs from departments such as advanced research computing, but the HR people, the money people, working out exactly how to transfer funds between institutions, to share resources, to share human resources in terms of where we can apply our skills and knowledge. And we'll also be advocating professional recognition policy changes via the Pro4RS working group and various other channels as well. We appreciate that we need to be talking to senior decision makers within the institutions, within funding agencies and so forth, to encourage this, to shuffle it along a little bit faster than it might otherwise be going. So I'm sure most of you will be familiar with the positive noises coming out of UKRI on this, which is part of the reason why this work has been funded in the first place. But I think there's more to do in terms of reporting back what we find and hurrying things along. So that is a quite rapid introduction to the Step Up project. Jeremy Cohen, it's Imperial, is the man in charge. I'm just kind of his sidekick on this one and standing in for him because he's at a different conference, I think, at the moment. But do feel free to write either to Jeremy or to me if you'd like to learn anything more about it. We don't have much in the way of project websites or anything set up yet, but that will be happening fairly shortly. So before too long, you'll be able to check in, and I'm sure we'll come up with some kind of newsletter or something to report on progress. So happy to take any questions that anybody might have at this early stage. Let me see if I can stop sharing my screen.
Has anybody got any questions?
There we are, there's the button.
No?
I've got a question.
Yeah, I guess we better.
It's a bit hard for me to hear at the moment. So if there are any questions, yeah, you might want to speak up or use the mic.
Yeah, no, I'm just sorting out mine.
Ah, cool.
We'll just use that one. Way easier.
Can you hear me, James, and other remote people?
Just about, yep.
I'll put the microphone a bit closer. So I'm just wondering, I mean, you talk about, I think you did mention training resources at different levels. Is this focused on new entrants to the research technology professional kind of role, or is it equally aimed at those of us who've been around for a while doing kind of more or less ad hoc collections?
Yeah, so it's a bit of both. Sort of old hands are not being neglected here. What we're looking to do is really bring the training and the career structures together. So looking at the different grades for each of the professions and thinking what kind of training is going to be most beneficial at those grades. So there will be a bit of looking at existing training for people who are literally just starting off in their careers in these kind of tracks. But there will also be training that's much more beneficial to people on the higher levels as well. So it's kind of a bit of a sort of a matrix approach to training. So yeah.
And sorry if I could just follow on if no one has got any other questions. One of the things with short-ish term projects like 4 years is what happens after that? Do the training resources get maintained? Is there any kind of planning for sustainability beyond this project?
I'm going to try and talk them all into making them carpentries lessons of some description, in which case there should be.
At least that gives a framework.
Yeah.
For people to take that.
So hopefully the communities themselves will have picked up on some of the kind of training that's been developed during the project, some of the work that's been done, and be able to take that forward just as part of the usual kind of professional structure for what we're doing. So hopefully it'll be quite a sustainable, maintainable set of outcomes by the end of the 4 years.
Any other questions for James? If not, I will say thank you very much, and I will ask for a round of applause for James, and then we will switch over to Ben.
I'm going to talk a bit about my experience co-leading a first-year programming course for students in the physics department. Firstly, why is it not showing me my notes? Sorry. I am sorry about the beginning delay. I'll move that out of the way. Right, okay. So I'm going to talk a bit about teaching the course and designing the course, which sounds a bit like it's the wrong way around, because we should presumably design a course before we teach it. However, generally, in my experience, we don't start completely from scratch. We get given an existing course, often at quite short notice, and we think, wow, there's so much that I could improve about this. And then we realize there's actually only 3 months before we start teaching, and there's not much time to be very ambitious because the rest of our job hasn't gone away and we still have a lot to do. So we have to really kind of choose 1 or 2 things to focus on and improve and just make the best run as smoothly as possible. So in particular, the first year that my colleague Becky Chislis and I took over this course was in 2020 to 21, which people may remember was not entirely a typical teaching year. We had to move all the existing content to online delivery, but we weren't told definitely that that's what we would be doing until very shortly before the beginning of term. There was a lot of work going on to prepare for possible online delivery or having to switch back and forth very quickly. There was additional software licenses purchased, for example, for CoCalc. The CoCalc license was finally confirmed that we'd have it on the Friday before our course started on the Monday, so we didn't use CoCalc. So I'm going to try and put this in a bit of context. Let me just get my phone so I can keep an eye on the time. I don't want to kind of overrun. So I'm going to explain a bit about the context of this course within the physics department and within the physics degree structure. Talk a bit about what we teach or try and teach and how we structure the course and how we deliver it, talk about some of the particular challenges that we have faced and continue to face. I'm going to talk a bit about the things that we have changed in the few years since we took over the course, and then talk about what we might want to change in the future, and then hopefully get you people to tell me what we should do so that I can copy your ideas and not have to do it all myself. And then maybe there'll be some productive discussion after that, for example, from people teaching computing courses in chemistry or any other departments. So just the physics degree program, there are some variations on this. For example, this is the first year of the straight physics degree. We also have an astrophysics degree program and theoretical physics, which have small changes in the second term of the first year, and then they diverge more later on. There's also a 3-year BSc and a 4-year MSci course, but again, they don't really differ in the first year. So in the first, there are basically 4 modules in each of the 2 terms. And there's a year-long module in science communication that kind of runs in parallel to all of these. So what I'm going to talk about is part of the first term module in practical physics and computing, but it is only part of that module. So this module also includes the actual lab experiments that students do. It includes our computing component, and it includes some teaching on statistics and data analysis. So each week in term time, apart from reading week, so there are basically 10 timetables weeks of the course. In each of those weeks, the students will spend 1 3.5-hour session in a lab doing an experiment of some kind. They'll spend 1 3.5-hour session in a neighboring lab doing our computing course. They will also have a 1-hour lecture on data analysis and statistics. So it is kind of widely recognized in the department, I think, that this is kind of too much to be fitting into a single module. And there are talks about how to restructure things and maybe spread it out over 2 terms. Of course, it's always easy to think what should expand, but it's hard to get people to agree on what should contract to make room for this. But I think within the kind of practical and computing side of things, we've kind of come to some almost agreement on that. But it is a lot to fit in. So it's a high workload, both for the students and for the staff teaching it. So a 15-credit course module like this corresponds normally to 150 learning hours. And for a lecture course, normally some fraction of that is spent actually in lectures, but a lot of it is in smaller group discussions, problem-solving tutorials, and probably the majority of it is just individual study time. And it's not just in the term that the course is taught, but over the holidays and into term 3, as the exams start, students spend a lot of time revising. We don't have that in our course because all the assessment is done within the term. So it's actually not really possible to fit those 150 learning hours in, but that's all right because they're only notional learning hours. What do we teach students? We teach them programming. A lot of them have not done any programming before. Some of them have run their own startups in AI, but they're the minority. There are some in between. But maybe surprising to me when I first started teaching the course, more than half the students we ask have not done any programming in school. Those who have sometimes done a bit of Python. A lot of them have not even used a spreadsheet, for example. They just they see computing devices as just a kind of consumer product, and they've not really engaged with them at a level deeper than that. So we want to get them from that, assuming no prior knowledge, to be able to use computing to analyze data, for example, So before reading week, we try to get them to the stage where they can take a data set, fit a straight line to it, take the errors into account. So some of these points are more precisely measured than others, and extract parameters, again, with corresponding uncertainties. And then after reading week, the second half of the term, we move a bit more onto computational physics. They use Euler's methods to look at problems like simulating orbits of planets. In later years, they get to use slightly more sophisticated algorithms and look at kind of more accurate approaches. But this is really get them from the starting point where they may not even have used a computer to calculate numbers. So we start with using Python as a calculator. We teach them to write functions and loops and comments and so on. We use Python because, well, why wouldn't you? It seems to be the kind of default option now. It wasn't necessarily, I mean, I was involved in other programming courses and in leading the computing strands, the kind of overview of computing courses in the departments years before this. And we had a mixture, especially in the first year, of Excel, Visual Basic, and MATLAB. We decided to converge on Python for many reasons, partly because it's freely available. You don't need to pay licensing to Microsoft or MathWorks, and students can then use it in their own work across the degree and outside. We use the Jupyter Notebook as a programming environment. I have mixed feelings about that. I think perhaps if you're teaching computer science, then it's not the ideal platform. It certainly shouldn't be the only platform. But for physics students, rather than software engineers or computer scientists, it does let you create notebooks which are nicely presented. You can write up and explain your results. You can include diagrams, as well as including and executing code. And we don't really have the time in those 10 weeks to start from beginners and teach them two different platforms, although before my day, they did use Spider or some other basic IDE for the first couple of weeks, and then they moved on to Jupyter Notebooks. But we just don't really have the time to get them up to that level of expertise in two platforms. So we now do everything in Jupyter. We don't use Jupyter Lab, which is a more sophisticated IDE, but implemented through a web interface, because it's just a bit too intimidating for a beginner. Jupyter Notebook has a much kind of lower threshold to get over to actually start doing productive work. So we were quite relieved there was a move in Jupyter to actually abandon the classic notebook and move entirely to Jupyter Lab. There was a bit of an outcry, and now the Jupyter Notebook has basically been re-implemented as a simple interface on top of the Jupyter Lab components, which is a relief to us. What else do we use? So within Python, the Python core language doesn't do everything we need. For a physicist, you really need to use something like NumPy, and some parts of SciPy we actually use for the statistical analysis. We use matplotlib for plotting maths and creating graphs, and indeed even some simple animations. Again, I have mixed feelings about matplotlib, as I do about any technology that I've actually used, but it's certainly, yeah, it's not bad, and again, it has quite a low kind of a threshold to get started. We use Moodle because we have to, because it's part of UCL's rules that you should use Moodle. To be fair, I don't think Moodle is worse than any other near equivalent that I've seen. I'm more familiar with its problems because I use it. I'm sure if we still use Blackboard, Collaborate, or anything else, I would hate those just as much. We use LectureCast, which is UCL's wrap of the Echo 360 platform, for distributing screencasts, kind of videos, because they're very popular with students. I'll probably touch on that a bit more shortly. And my last minute addition, we also use something called JPlag, which is a Java implementation of a kind of plagiarism detection system. Turnitin really doesn't work for computer code. JPlag kind of works, and we usually catch a few cases each year and pursue the most blatant ones to encourage the others, as they say. How do we teach it? So as I've mentioned, we teach in our teaching labs because that's the only place we've got enough PCs to have one per student. I have taught in classrooms around UCL in the past, but there aren't enough of them to keep up with demand. Our teaching labs are not ideal as a teaching space. They've got pillars that block your view. It's hard to address the whole class at once, but that they are there. The desktop at UCL PCs we have work reasonably well. Desktop at UCL, people can also use the desktop anywhere system. They can use the same system remotely. So it works okay. So each week we get them into the lab. They're divided into groups because we typically have 200 or 300 students in a year and only space for about 65 at a maximum at a time in the lab. We give them some notes to read. We make some of them into videos and try to encourage them to bring headphones because otherwise I have to listen to my own voice from 20 different directions as I'm in the lab. We give them a quiz each week to try and test what they've taken in, and they can reset that as many times as they like. We give them a programming task, which is part of their assessment. And then we have a bunch of demonstrators who are a mix of academic staff and postgrads who walk around and try and help students. They also have 2 longer assessments to complete independently outside the lab. They're supposed to do them independently, but of course there's a limited amount of say we have in what they actually do. For the final assignment, we do give them help with the first part of that in the last session of the course, and some of them actually turn up and take advantage of that. So some of the challenges we face are what seem like to me like large student numbers. A few years ago, when I helped as a demonstrator on this course, we had about 180 students in 3 groups. When I took over online, we had 200-ish, I think, but it didn't matter so much because we didn't have to fit them all in one room, although we did have to provide remote tech support to 200 students installing Jupyter Notebook on laptops, having never done any programming before. It actually worked surprisingly well. I mean, obviously we had less time to help with other things maybe, but it kind of worked. The largest cohort we've had is about 300, which was the year after COVID, when all the A-level exams were scrapped and students who already had conditional offers to get into UCL suddenly all got higher grades because it was assessed by their teachers and not by exam. So we had 5 sessions a week instead of 3. It's gone back to around about 220 now, which just about fits in 4 sessions a week. As I've mentioned, they have a variety of prior levels of experience. Getting them to engage can be quite difficult. We really, although we want to stretch the more able students and the ones with existing knowledge, our absolute priority has to be to help the ones who have not done computing before and are really quite anxious about the whole thing. So that in-person teaching and being able to go around and look over their shoulder and help them is very valuable. Getting them to actually ask for help when they need it is quite difficult, though. It does involve some kind of badgering at some level to get them to actually ask questions and discuss what they're doing. Assessment is a continuing theme. We're constantly being told we assess too much. On the other hand, there is a lot to assess in this course. So given that this module has lab, stats, and computing modules, and yet we're told that we should only have 1 or 2 assessment components, clearly that's not going to work. And it is true that our computing component has more assessment components than the other parts of the module, because we have both weekly assignments, which they do in the session, as well as those 2 longer assignments that they do in their own time. I would like to do less assessments in a sense of summative grading, but the feedback is very important. The reason we've resisted getting rid of the weekly assessed tasks is because it really is part of the actual learning experience doing those tasks. And experience has shown that the only way to get students to actually turn up and engage with those is to make it worth some fraction of their final grade. Availability of staff and PGTAs to help, again, changes over the years, but budgets are tight now, so we have kind of less help than we used to. And some of the academic staff who were pressed in by the department to help at late notice had never actually used Python before and not programmed a computer for 12 years. They all did an excellent job of catching up and doing their best to help, but it does show that there are challenges for everyone involved, not just the course module leaders and not just the students. So what have we changed since we took over the course? Well, in the first year, we had to make it all work online. That took up all our available effort for the full year, basically. Then the next year, we had to switch it back to in-person teaching for a record-sized cohort. So that took a lot of work. The third year, I finally managed to get rid of one of my technical bugbears, which was VPython, which lets you create animations in a nice, simple way, but also just fails randomly. It's very hard to debug. And we decided that we would use matplotlib animations instead, which I now hate almost as much as I hated VPython, because there's just so much boilerplate you need to give the students and just say, use this, and you try and explain how it works. And anyway, there you go. Fourth year, I finally managed to actually teach them about functions earlier, because I think functions are good and students should know how to use functions. I also had the naive idea that maybe we'd be able to introduce more automatic grading and feedback for some of the simpler tasks, because once something is a function, you can test it with multiple different inputs. Haven't got that far yet. And then we were heavily leaned on to speed up our marking, not improve or make it. The students mostly complained about consistency and perceived inconsistency. However, the department is in special measures or whatever it's called because of late feedback. So basically, we'd had to redesign everything to get everything, these assignments marked very quickly by a group of academics who had, again, been press ganged at the last minute and weren't terribly keen on the whole idea anyway. So we did just about manage to get our feedback to students within the UCL deadline for at least one of our 2 assignments. Yay. So what else do we want to do? What else do we want to change? These questions are the same questions that you'd ask if you were starting a course from scratch, largely, because I think course design is a kind of ongoing process. We're always designing the course at the same time as we're teaching it. What do students actually need to learn about computing? They're not computer scientists. Some of them will probably be software engineers, but most won't. They are being taught to be physicists. What do they need to know? What is AI going to make obsolete and what is always going to be needed? I added a special slide on AI after this, so I'll come back to that in a moment. And how do we assess what they've learned? I really want to spend all my time talking to them and giving feedback and helping them learn. But at the end of the day, we need some summative assessment. We need to say this student has learnt what they needed to learn to some standards. But what's the best way to do that? We don't want to impose too much workload on the students. We don't want to impose too much workload on the staff either. I think the assessments that they're completing shouldn't be just extra workload for the students. They should be learning from doing it. But that kind of leads you in the direction of having to have very so-called authentic assessments where it's open-ended and then it's a nightmare to mark and it takes a long time and it's very hard to be consistent. I've been reading a lot about, alternative grading and so-called ungrading, specifications grading, where instead of having very fine-grained judgments, you have like, did they reach this level or not? Again, there's a lot of work to actually implement something like that and to make it compatible with UCL's academic manual. Anyway, so what do they need to learn? How do you know when they've learned it? What do they have to do? What do we have to help them to do to learn it? I think the key to all this is the last point. We've got 200 or 300 students, but they're all individuals, and they keep a common complaint from students in most courses is, well, I didn't understand this. You didn't tell me how to do that. And I've seen people madly trying to add notes and add videos to try and explain to them all these things that they don't understand. But then you've just got students who are overwhelmed by the amount of stuff that's in front of them. Really, you need to try and figure out what each student already knows, what that student doesn't understand yet, and help guide them to the video or the notes that they need and give them the feedback that they need. That's still a very kind of a labor-intensive process. And maybe AI will help with that in the long term, because AI is going to change everything eventually, maybe, but not really, because we've kind of been here before. If you've been around a while, there's always some latest buzzword. Students still need to learn something. I mean, they wouldn't be students if they weren't learning something. What they need to learn depends on what their aims are. If they've chosen to do a physics degree, what do they need to learn about computing? It might not be the same as they needed to learn 5 years ago, but we're still a university, not a training college. We're not training them to fill some well-defined role, to use some well-defined toolkit. We're trying to, yes, give them a defined toolkit that they can use in their practicals and fit straight lines to data, but also teach them enough of the underlying principles that they can apply that to different toolkits and kind of go beyond that. So the students still need to learn stuff. They still need to learn it, I think, from experts. I would like to delegate more of my work to kind of technological tools, but it's still a lot of work to actually plan that and to make it work and to make sure that the tools are giving reliable results. Yeah, large language models are the latest thing, but they've got an advantage. They've sprung onto the public consciousness, having absorbed the last 20 years of experts pouring their knowledge and their work onto the web. They're basically automated the plagiarism of all that work that's already been done, and now they're kind of consuming their own output increasingly. I think there is already a level of diminishing returns there. I'm not saying that it's the end of the road for LLMs. I'd also say there's a lot more to AI than large language models. And I'm more interested in the other approaches and combining toolkits where we can use existing like unit testing frameworks to test software, but combine that with some kind of expert system, if I can use old-fashioned terminology, to actually identify what misconceptions are being shown by the students who submit this work. So anyway, there's plenty to read. I just stuck some random screenshots that I've been reading recently on this morning, saying, yeah, we need to completely change what we teach. There's many papers telling you how to redesign your entire course using AI, but it's not as simple as that. There's an interesting paper on getting students to generate code by prompting an AI. They're not able to actually enter code. They have to just edit their prompt to a slightly modified AI. And surprise, surprise, they find it really difficult. You might as well just teach them to write Python, to be honest. Anyway, I've probably gone over my allocation, but James went under his, so, you know, we're all friends here. So I'm hoping that there'll be some discussion and people will tell me what I'm doing wrong, ask me questions. Maybe we can start some ongoing discussions about how we can work together in different departments and what we can all do better. That's it.
So, yeah. So what questions do you have for Ben? Please feel free to unmute yourselves and put your camera on if you were in the room. I can see Davida's put his camera on. I'm guessing he may have a comment or a question. No, he doesn't. So for me, the AI thing is fascinating because we let our students use free versions.
Yeah.
And it was interesting what they came out with.
Yes.
And that bit about the de-emphasizing the syntax is that if you haven't learned the syntax, how do you know that what is produced is right or wrong?
Yeah, I think that is
because it produces an awful lot wrong.
Yes. And I think, I mean, even before the latest LLM craze, because we're teaching physicists and we're teaching them to do scientific programming, I mean, in any kind of programming, testing is key. You want to know that it's doing the right thing. If you're writing a finance user interface or a finance system, it's probably fairly clear what the right answer is. I would like to think so. But in physics, it's not so easy. But teaching them, to think critically about their own outputs or the output of an AI is still important. I almost forgot to include my AI slide, even though I've been thinking about it a lot, because it doesn't really answer anything, to be honest. I mean, it's another set of tools. AI, in the broader sense, includes a lot of kind of tools that we're already using. Sorry, I got a bit distracted. I've gone off at a tangent. UCL, of course, has provided some rather vague guidance. The one concrete thing they've said is that we have to decide for each assessment whether you allow AI use, ban AI use, or make AI use a kind of key part of that assessment.
There's another change coming.
Oh, don't tell me. No, do tell me. But I could in a moment. So most of my colleagues have gone for banning AI. I'm defeatist enough to know that we can't stop them from using AI. So I've said you can use it. You can only use freely available tools because otherwise it creates an uneven playing field. I don't know what they're using. I haven't spotted any telltale signs of LLM generated code. And I have spotted the telltale signs of good old fashioned plagiarism and collusion. As with other forms of cheating, I think the students who feel that they need to cheat are the worst place to cover their tracks, and they're generally quite easy to spot when it comes to dodgy code. But yeah, I think a key part of the summative assessment is knowing who's done the work. And some students will say, well, we're going to be using AIs in real life. Well, yeah, you're going to be using calculators, you're going to be talking to colleagues, but we still want you to be able to do something yourself, not just copy colleagues' work. Someone needs to do that. But I'm interested to hear what the change is going to be.
So the senior education team have put a paper into EdCom, but I think has been signed off and it's coming. That 50% of the program in a year has to be AI free. So that has to be either some sort of Fiverr presentation or written exam. But if your other modules are covering that, you'll be fine. Where we have modules that are not part of programs, they are standalone. We can no longer do 100% course work because the team is individual work. So there is a minor change to be submitted by July. There are bigger changes to be submitted by next March and bigger things.
Okay, that's interesting. I mean, I am quite a big believer in locking students in a room and sitting them down to do an exam, just because it is the only way you really know who's done the work. Yeah, okay, that's true.
Well, I mean, maybe that's what you meant, but just to avoid any misunderstanding. My understanding of that policy is not 50% of it must be AI proof, but it must be proof, well, must avoid any misconduct based on it. Right? So if you have something that is using AI but in a legitimate way.
Okay. So for programming, given that it's built into GitHub, it's built into VS Code, it's almost impossible for them to do a coding assignment without AI assistance.
Yeah.
But I don't think that contravenes UCL policy.
They,
given that it's
they're
not-
changing, they're tightening the policy.
My understanding of that paper, I don't know. I guess this shows that it's not tight enough that it's
Yeah.
to be interpretation proof. But my understanding was the thing they take objection to is specifically misconduct to do with AI. So making work faster your own when it's not privileged. But if a co-pilot didn't make that with that. But
What is AI proof anyway?
Yeah.
I can memorize stuff that I've learned from ChatGPT and then word verbatim in the exam. Like, how AI proof is that?
Well, I don't know. I mean, you need to internalize it at some level, and maybe you'll learn something from memorizing. It is very hard to, for most of us, to memorize stuff we don't understand. So I don't know. There's a whole massive discussion that we could have there. Physics has certainly gone for, because a lot of our courses are pen and paper and solving things mathematically, and they do lend themselves to written exams. And as a department, we have leaned very heavily on that and insisted on having exams in Excel. So I probably will still have to assess entirely on coursework in this course and somehow try and satisfy myself that it's the students' own work. I mean, yeah, we should viva them all, but you know, if you've got 220 students, where are we going to get the time from?
I do think the point about
Do you mean it? Do I need to put the microphone on, or can we project a bit more?
Or shall I?
You want me to really speak up like an actor?
Do you want?
Yeah.
Would it help if they have that, or is that not going to help
Wait,
because it's
huddle
just
around.
going to be?
You kind of want people, yeah, that might help. The things are with his headphones, so I'm kind of like.
Oh, I see. Yeah, I feel like one slide ago, you were asking something about what should we spend our time teaching the students when they come to us with questions about, oh, you haven't taught us this or that. And I think this links quite tightly to what you were saying about AI, where a key skill in learning to program is learning to look up stuff for yourself, because you're actually doing that most of the time, well, a lot of the time that you're really programming. And already like widespread generative AIs, we as a field, I don't think did a very good job of teaching people, this is how you parse a Stack Overflow answer, or, you know, that sort of stuff. And we are going to have to learn to do that. And also now for prompting AI, I have no clue how to do that.
Yeah, I mean, yes, we need to encourage students to ask for help, and we need to teach them how to get help and how to ask for help from experts without wasting experts' time and putting people's backs up. Being able to frame a question well and getting them to boil down their long-winded piece of code to something that illustrates the problem, which itself involves some technical skills.
Yeah.
And one thing that I've noticed students tend to do when they have a problem is keep adding to their code to try and make it work. And what I try and encourage them to do is take things away and then get something very simple that works but doesn't do much, and then add it back a little bit at a time. So yeah, that I think is a skill that will stand the test of time beyond the specifics of prompting ChatGPT, which will change over the years.
It's that criticality and that being able to critically solve a problem and think about stepping through.
Yeah.
And this is one, I'm surprised at the variation in the skills that are coming in. Given what's currently in the UK national curriculum, in the one, they should all be able to use spreadsheet and they should all have been exposed to some Python.
Yeah.
But we're losing, well, I mean, certainly, I mean, there is something they should have done pre-2012. There are changes since 2012. I mean, you know, the weird people writing the 5-year-olds, but they're not teaching them problem solving.
Yeah.
And that there's no critical thinking. A lot of that is being pulled out the critical point where someone's discussing being interviewed at school, there wasn't allowed to be techniques like think, pair, share. So students were not allowed to discuss in the session, even under the teacher instruction.
Right.
It was that a student could the only time a student could talk at any point in lesson was in response to a direct question from the teacher. The teacher was not allowed to use discussion after the lesson.
Yeah.
And this is secondary. And this is now England. So I think we're going to have increasing problems with first years in that communication piece I think is not there, that thinking isn't there. And I think that problem solving is going to continue to diminish to the point where we're going to have to teach them how to critically think and how to think.
Yeah, which is, I mean, an impossible problem, really. You can't exactly teach people to critically think. You can teach them in a particular context, I think, and that's all we can really do is figure out what are the sorts of problems we want them to solve, and then maybe they can generalize that, or maybe they can't. But yeah, that what you talk about, think, pair, share, and actually getting them to talk to each other. And we don't explicitly do that in our sessions, but we don't discourage them. We tell them that they're welcome to talk to each other, but then maybe we're sending slightly mixed messages, because then we say, but your work you submit has to be your own. And of course, there isn't really a clear distinction between what's your own work and what was collaborative. If you've been talking about something, I mean, if someone else says, oh, I did it this way, and it's a better way than yours, then you should use that way, but you shouldn't copy them. But what does that mean? You have to type it in yourself. You have to use different variable names. I mean, where do you draw that line? It's difficult. But again, I don't want to spend all my time thinking about assessment and avoiding plagiarism. I'd rather be giving them useful feedback.
Can I all of that? Yes, I have no answers in the same questions, and I have yet another question, which is so you managed to do something that I wish we did in chemistry, which is to have a bit of programming as soon as they basically walk in the door of the degree. But then I guess it's difficult to make it clear how useful it is later on and to reinforce that learning if you don't then echo specifically those technologies like Python in those same contexts.
Yes.
But later.
That is part of the rationale between the fact that the reason that we decided as a department we would use Python is that now I don't know how it's done in other departments, we have these things called strands where related courses, like there's a computing strand, there's a quantum mechanics strand. So the courses in that area over the different years have regular meetings and discuss how to make things mesh together. So we use Python throughout, except for one course for theoretical physicists where they use Mathematica, and I wouldn't want to try and re-implement that in Python. Unfortunately, that course may die a death anyway. But of course, we also want to get them to use Python, use programming skills beyond the programming courses.
Yeah.
And yeah, we can encourage them. We talk to other lecturers. Some lecturers in other courses have actually created or got students to create Jupyter notebooks to illustrate concepts. And it's great when they do that. Part of the advantage maybe of having this module with too much in it is that at least it forces us to talk to the lab people and the stats people, and we make sure that we're all reading from the same hymn sheet, and we used to teach them straight line fitting in Python, and then the lab demonstrators would do whatever they wanted, which was usually show them an Excel spreadsheet and get them to do it that way. Now we've kind of put an end to that. They do actually use the same toolkit across the components.
But presumably in the first year lab, they still do data entry in some spreadsheet software.
Yeah, I think they probably mostly enter in Excel, but then I think what they're now encouraged to do is then save it as a CSV file, and then they read it into Python.
Then it's nicely reproducible in Python. You can get your error bars and everything. It's just on to do that.
No, I remember trying to teach error bars and error straight line fitting in Excel, and it was painful.
That's in Excel.
Yeah.
And I would teach it to people, and I go, please don't actually need to do anything.
Yeah.
I was a UCL physics undergrad in I think the final year that it was the computing module was half Excel, half MATLAB.
Oh, right. Wow.
Sort of
Okay.
stuff.
Yeah.
Yeah. And so I remember learning the straight line fit in Excel.
Oh, bad luck.
And yeah, but then, so what was the timeline? Because I know that there was a third or fourth year Java.
Oh, I taught that. Yeah.
Yeah.
Yes, that's gone. That was again a course that I took over and then tried to kind of evolve rather than redesigning completely from scratch. So that was the focus was object-oriented programming as a kind of more structured approach. That's now been replaced by a machine learning course.
Oh, okay.
Which uses Python.
Yeah.
So there you go.
C++.
Well,
That too.
the year I took over was the year that, well, the Python course I didn't take over. I was assisting. That was my first year at UCL, and the person who had took it over had just converted it from C++ to Java because that was what they knew. I like Java. I'm
Hate Java. Not everything needs to be an object.
no, but yeah, I mean everything in Python is an object. It's just that you don't need to care very much about the fact that it's an object. Java does involve a lot of boilerplate, which admittedly I don't like. I do quite like the idea of teaching them a statically typed language where they actually need to decide what this object represents rather than just hoping that it does the right thing. But at least it's not JavaScript, so you know.
So I was a computer science undergrad. So we taught effectively C.
Yeah.
Then the C++ bit, and we were banned from writing basic and other things. So it's like basically anything where you can do the things you do Python, you just change the data type, music.
Yeah.
That was just like banned.
Yeah.
So I kind of go, I get Python.
Yes.
At the same time, part of me thinks it's still inherently wrong.
Well, it is. Yeah. I've come to terms with teaching the wrong things.
I mean, and I should say about because
David has raised his hands, by the way.
Let's get David.
Yeah.
No.
Thank you. Cool. Okay. So, Ben, you were saying there, one of in the last slide or something, you have something like how can we collaborate, and I don't know the person next to you that was talking about chemistry, but it seems that I think there is a kind of opportunity of which is something I would like to do, which is to kind of discuss between all the people who are teaching some kind of similar things and see whether we can reuse the material that people are creating and reuse like the exercises and the quizzes and the things across the different modules that are teaching similar things to do with Python or any other programming stages later.
I'm not sure I entirely agree, because I think what we are trying to do is tailor our course very much to physics students in our department, rather than teach them so maybe for the very beginning when we're teaching the basic syntax, I think that's true. I mean, across other sciences, maybe they're using straight line fitting, but you know, we try to illustrate it using Hubble data, for example. So I think there's always going to have to be quite a lot of tailoring of things going on.
Sure, but still, if we share that information across, it will be easier for people to get ideas of saying, okay, if I want to, you know, a semester from biology and I see your example, or I see what you done after the basics that we know that everyone knows the same, you know. So there's the thing of the basics that it would be good if everyone has kind of a common curriculum in a way, and then the extra bits that are different, it may be, as you say, different, but it would be good to even to collaborate on them so that they could be reused. Even so, for example, you say physics, but even if it's a medical physics student that are doing some image analysis, it doesn't matter whether it's a Hubble image or it's a something else, for example.
Yeah.
So I'm wondering how we can do that.
Coming and giving this talk is part of trying to share ideas. Whether it goes beyond that to, you know, sharing specific materials, yeah, I don't know, because there is a lot of overhead involved in just that kind of coordination between people as well. So I think certainly where it comes to tools and whether we can actually between us find or tailor a kind of a chat bot that can actually give useful answers to Python programming questions, that would be cool.
I'm
Yep,
just
can I-
thinking of time. Fabulous. So let's wrap up this formal bit. I'm going to stop the recording, and then I will leave the Zoom open, and then if people want to chat, we can have coffee and be sociable and things.